Today I will talk about octahedral point group example. So we will solve this example and I will try to show the octahedral splitting by using group theory. So to do that, firstly we should select a molecule, and this can be our molecule, sulfur hexafluoride. So this molecule has an octahedral geometry or octahedral point group. We can draw the molecule. It is very symmetric. We have F atoms around the sulfur atom. So sulfur is our central atom. And we have sigma interaction, and we have also pi interaction. So pi interaction is not important, but I want to mention it. So for instance, we have a sulfur and we have a F atom here, and we have a, for instance, pz orbital, right? This is the plus sign, this is the minus sign, and there might be an interaction with the p orbital of the s, and this is simply our pi interaction. But again, this part is not very important. Therefore, we can only consider the sigma interaction for our case. And sigma interaction can be represented something like that. So we have a plus sign here, we have a minus sign here, we have a F atom, and there's a minus and plus sign of the orbitals. So this is our sigma interaction. And basically we have 6 LGO, which is due to the sigma interaction, and we should have 12 LGO, which is not important. We will not consider it from the pi interaction. And we need a reducible representation for the 6 LGO for the sigma interaction. And we also have to know the symmetry for the sulfur atoms. So as you know, for the valence region, we have 3s orbital for the sulfur and 3px, 3py, and 3pz orbitals for the central atom. So these will be used to construct the molecular orbital diagram. But the issue is that the 6 LGO reducible representation is not easy to see. The reason is that octahedral geometry might be complicated. So firstly, I want to talk about the octahedral point group. We should try to see the symmetry elements before write the reducible representation. I want to draw the molecule here. We have a central atom and we have 6 ligands. This is the y-axis, this is the x-axis, and this is the z-axis. In octahedral point group, and you can look at from the internet or somewhere else, we have a E operation, 8 C3 operation, 6 C2 operation, 6 C4, 3 C2 prime, or this is also can be written as C4 square, of course. Inversion, 6s4, 8 S6, 3 sigma H. I need a little bit space here. 6 sigma D planes. So how can we see them easily? So E means, as you remember, do nothing. And so I'm basically trying to make the LGO. So I am just looking at the sigma bonds and this is just the sigma LGO. Maybe I can write something like this. Of course, the issue is that trying to see the symmetry operations. So basically E means do nothing. So all the bonds will stay in the same position. So we can write as 6. And we have a C3 operation. And to see that, actually, I want to draw it here. So C3 might be a little bit hard, but we have a triangle here, and we have another triangle here, and C3 actually is from here to, maybe I should use a different color, black, from here to here. So we have C3 here, and we have so many of them. Actually there are 8 C3 axes. So basically we have 4 triangles. We have 4 triangles like this. So I am just considering this as 1. Okay. And we can also rotate it 2 times, right? C3 square. Therefore we have 8 C3 axes. But just considering 1 is enough, as you know. So if we apply the C3, all the bonds positions will change. So it will be 0. And we have C2 axis. And seeing C2 is also a complicated one. To do that, I will draw a cube. Okay, I will draw the cube. And I will put the molecule inside this cube. So ligands are on the center of the planes of the cubes, and we have a central atom somewhere here. And C2 axis is actually passes from here to here. I hope you can see it. So it passes from the center of 2 edges, and we have 6 of them. And basically if we apply this operation, I think you can see that it doesn't include any bonds, since it basically passes from here to here, right? It doesn't contain any bonds, and if you apply it, all the bonds position will change. Therefore this is basically 0, but I want to delete it. So basically this is 0. Then I want to show so this was for C2, this was for the C3, and I have to show the maybe C4. It is very easy actually. C4 is from here. This is C4. And if you apply it 2 times, it will again be applicable, and therefore there should be 6 of them, since we have one of them here, the other of them here, the other of them here, and you can apply all of them 2 times, since this is C4, and it contains 2 bonds. So you can apply one of them, and you can see that it should be 2. And this was C4. C2 prime is again from here. This is C2 prime, and it contains the 2 of them, 2 bonds. So again the answer should be 2. We have an inversion. Inversion is again from here. If you apply it, it should be 0, since after the application of the sigma h, so you know E operation is C2 times sigma h. So there's a plane. After the operation of the plane, bond positions will change, therefore it is 0. S4 is from this position again, since you can rotate it to 90 degree and apply the sigma h. So S4 equals to C4 times sigma h, as you know. So it is again 0. We have S6. Seeing S6 might be hard, but it is the same logic. So we are, for instance, if we try to apply it, we put this thing here, since we rotated 60 degree, right? And if we apply the sigma h, it will come here, and this is the S6 operation. Of course, after the application of this, the representation should be 0. Sigma h contains the four bonds, so this is simply sigma h, right? So this should be 4, and sigma d again is very similar to C2, and it contains from here to here basically this plane, and it contains the 2 bonds. After the application of the sigma d, 2 bonds stay the same position, so this is basically 2. I don't want to waste more time. The reducible representation equals to A1G plus EG plus T1U. So it is very easy. So we know right now 6 LGO reducible representation, and I wrote something like this. It was equal to A1G plus EG plus T1U, and these two might be very familiar to you. If not, you will see in a few minutes. And then we need to make the representation for the central sulfur atom. So in this case, you can consider the two main orbitals. The first one is 3s orbital, and it is totally symmetric, therefore it should have A1G symmetry, right? And we have 3px, 3py, and 3pz orbital, and they have T1U representation. So if you are not sure, by the way, so these are the central atoms. You can look at the octahedral point group table, so it should be clearly written. So we know the right now reducible representations for the central atom and the representation for the 6 LGOs, and I want to construct the molecular orbital diagram. So we have 6 F atoms, so 1, 2, 3, 4, 5, 6. So these are our LGOs, and we are just considering the sigma. We have 3p orbitals of the sulfur atom, and we have one 3s atom with A1 symmetry, and this one has T1U symmetry. And LGO symmetry was this one, A1G plus EG plus T1U. So EG is double degenerate, so 2 orbitals with same energy, and T1U is triplet, or so 3 orbital has the same energy, triple degenerate. But we don't have EG here, so the EG is actually non-bonding orbital. Right, this is the EG, and it is non-bonding, actually non-bonding. So this T1U and T1U, the other one, can make a bond, and there should be also antibonding interaction, right? Maybe I can write it as T1U sigma star interaction, and this is T1U sigma interaction. So we have A1G. A1G splitting should be very, very high, since the energy difference is high. So we have A1G here. This is again a sigma interaction, and we have A1G star around here, which is anti-bonding, but I want to write it as sigma star. Okay, this is sigma star, and this is our molecular orbital diagram for the sulfur hexafluoride. So we can put our electrons. If you put it, it will fill until here, by the way. So this is our highest occupied molecular orbital, and this is our lowest unoccupied molecular orbital. I think there is a small correction. This is lowest unoccupied molecular orbital, but the issue is that I think this is little bit lower in energy, so our A1G is here. So this is A1G, this is the other A1G, and this is the interaction. Okay, so our LUMO is here, so this is our LUMO. Sorry for this small mistake.